Welcome to the Potter's Roundtable, a monthly podcast where we share our passion for the ceramic arts and a collection of topics specific to potters. Remember to subscribe so you don't miss a single episode. Enjoy the show.
Okay, today's topic is, I called it Pottery Figurin, but basically it's going to be about how math, some simple math calculations and how math enters into pottery. I was doing some glaze calculations myself recently, and I realized that, it's something that you almost never talk about. We have all these little sort of different areas where you do a little calculation of either for glazes or for density or specific gravity or something like that. So I thought this is the reason, when I sat down and thought about it, I came up with about a dozen or 15 different sort of actually little calculations or areas where math is useful. So I thought that might be good to assemble them into the talk. So that's how this sort of evolved. I was doing it myself and I thought, hey, we've never talked about that. So basically, and this is all part of what I was talking about earlier, where there's a lot of science and technology and math in art, and we bump into it, but we don't think about it so much. And especially for ceramics, which is so process related, I think it's really useful to know, at least have a little bit of an understanding of some of this more technical background. It doesn't have to get in the way of the aesthetics, but at least it's useful to have it. So anyway, we're going to start out with a few simple things. So first of all, I just want to review some really basic things. The idea of what percentages and and this is for people that for math that was a long time ago. Basically what fractions and decimal fractions and percent is, because that's going to be an important comment. So basically, you're all probably familiar with, a simple fraction like 1/4 can also be written as what's called a decimal fraction, which is that. That's the same thing. This is 1/4 or 25. And this is also the same thing as percent, 25%. It's all the same thing. Because this 1/4, this is, when you write a decimal fraction, like this column is tenths and this is hundredths. So this is actually 25 100ths written in a decimal form. Well, that's the same thing as 25%. Okay, so we're going to be talking about, and we won't be using sort of ordinary fractions a lot. We do sometimes, but we'll be using a lot of decimal fractions or percentages a lot in a lot of these things we'll talk about. The other thing I just wanted to mention early on is that for a lot of the things that we do in pottery, especially when you're dealing with glaze calculations, you need to use the metric system. Because the whole system of chemistry is based on the metric system. So we'll get to a couple of these later. They're not very complicated, they're simple ones. But we have to go back to using the metric system. So instead of using the English system that we're probably more familiar with, is like pound for weight is pounds and ounces. Well, in the metric system, it's going to be kilograms and grams. And the conversion there, just to sort of review that a little bit, the conversion is 1 pound equals 453.6 grams. So a gram isn't much. A gram is actually about the weight of a paper clip. An ordinary paper clip, that's about what a gram weighs, or what a gram is, okay? So there are a lot of, for instance, when we talk about making up glazes, you can make up glazes using pounds and ounces. You can use any unit you want to. But when we actually start doing calculations where we want to get into, we'll talk about molecular weights and maybe substituting materials, then you have to go to grams, because then we're not just doing percentages, we're getting into chemistry, and we need to use the metric system. And we'll talk about that a little bit. And the same way, in the English system, we're using feet and inches, whereas in the metric system, we use meters and centimeters. And so the conversion there is 1 inch in the English system is 2.54 centimeters. And a meter is basically 100 centimeters. So a meter is slightly longer than a yard, like a meter stick, slightly longer than a yardstick, and it contains 100 centimeters. So an inch is roughly 2.5 centimeters, about that long. And then the other conversion we also do, even although we don't do it for these calculations, is, again, when you're doing technical things, for temperature, you're using centigrade or Celsius, not Fahrenheit. Pottery, because of its background and how it's sort of evolved, everybody talks in degrees Fahrenheit, degrees F. But in the scientific world, everything is done in degrees C. And their conversions, we don't have to go into that now. If you're interested, I can do it. But there are very simple conversions between degrees Fahrenheit and degrees centigrade. When you get to higher temperatures, as a really rough approximation, the degrees centigrade is roughly half of what it is in Fahrenheit. Really roughly, I mean, in a rough sense. But anyway, and we don't have to talk about that so much for this, but just to let you know that, again, when you're talking about scientific work and technical work in ceramics and in engineering, you'd be using centigrade. We don't deal so much with liquid measures when in ceramics, but again, the English system, for instance, would be quarts for liquids, whereas for the metric system would be liters. And just so you know, a quart, 1 quart is 0.95 liters. So a quart is a little smaller than a liter. You probably know this if you go buy wine. When you go buy wine and you get a liter bottle of wine versus a quart of wine, a quart is a little less than a liter, or a liter is a little bigger than a quart. But we're not going to deal so much with things that we work with liquid quantities. We're going to be using mostly weights and distances. So as an example, going back to percentages, if I have, this is, let's say, a list of something, let's say for like a glaze ingredient. If I have a list of ingredients and I have a list of quantities that look like this, 30, 50, and 60, the total is 140. If I want to know the percentage of each one of these out of that, I divide each item by the total. So if I want to know if this, let's say these are pounds or grams, it doesn't matter what the quantity is. If I want to know what the percentage of this ingredient is, if I divide 30 by 140, I get 21.4%. Actually, when I do the division, I actually get 0.214, a decimal fraction, which is the same as 21.4%. But if I divide 30 by 140, that's what I actually get by the division, 0.214. But that is the same as 21.4%. Everybody follow that? There are 3 areas that we're going to talk about today in terms of the math. The use of math for work that we do with glazes, math in relation to things that we do like with fired pottery, like for instance, how do you calculate percent water absorption to determine how porous a ceramic is? And then also just one final comment on kiln operation, which we'll talk about what's the best way to calculate the efficiency of a kiln. People are always talking about, oh, my kiln's a lot more efficient and you hear that a lot, especially with people that do wood firing. They're always comparing how efficient their kiln is, and we'll talk a little bit about how you actually calculate that. And it's very simple, but people don't talk about it a lot. I don't know whether have you all heard of like the Seeger glaze formulation? It's another way of expressing the recipe or the formula for a glaze, but you use molecules or moles rather than weights. And unless you have a question about it, I wasn't planning on talking about how you convert a Seeger formula to a recipe, or the other way, a recipe to a Seeger formula. It's an involved calculation. I can talk about it if you're interested. The reason why I don't do it a lot anymore is because there are great computer programs out there to do it automatically. So nobody does it longhand anymore. It's a very useful calculation because the Seeger formula, you're expressing the formula for a glaze in terms of the numbers of different kinds of molecules. So you can work out the proportions between how many molecules of aluminum oxide do I have compared to the number of molecules of silica. And that directly relates to the way the glaze performs, like how easily it melts, how runny the glaze is, what temperature it melts at. And so the Seeger way of writing a formula is really useful for understanding how the glaze behaves, what it does, which is not so easily just looking at a recipe. But a Seeger formula is not useful for actually making up a glaze, for weighing things out. So it's very common, you can take a glaze recipe, convert it to the Seeger way of expressing it to understand what the glaze does. You can tell by looking at a Seeger formula, for instance, what temperature the glaze is fired at. You can tell whether it's runny, you can tell whether it's matte, you can tell whether it's satin just by looking at the way the glaze is organized. But you can't make up the glaze. You have to convert it back to weights or pounds or ounces or percentages in order to make it up. So there are procedures to convert one of these formats to the other. As I say, you can do it longhand, but nobody does it longhand anymore because there's a lot of glaze calculation software out there. I use one called Hyperglaze that I like a lot. But there are these glaze calculation programs that you can buy that do the conversions for you. Mine, I think, was like $150 or something. You get a CD. And matter of fact, with the one I got, even he sends out once you've bought it, he sends out upgrades periodically, so you get the latest version. And you basically just plug in the numbers and push a button, and it does this involved calculation, which otherwise would take you an hour and a half by hand, in a couple of seconds. So I don't talk. I mean, we can talk about it again. If somebody has questions about it, I think afterwards we can talk about it. I'm not averse to it, but I wasn't going to spend a lot of time on that right now. Okay, so let's go into glazes. Glaze. First of all, one of the important points about glazes is that there's a proper format in which a glaze recipe should be written. And a glaze written should be written in terms of weight percent. So I should have a list of ingredients and it should be written in terms of percent. So this would be like maybe 20% and 30% and 50% equals 100. And then this would be the recipe of what's called the base glaze. And then anything else that's added to it, like colorants, something that's added for color, or something that's added to make it an opacifier, those are all additions to it. Those are not part of the base glaze. So the proper way to write a glaze recipe is to list the ingredients in percent, and it totals 100% for the base glaze, and then you say, then plus additions of whatever the colorant is, if there's an opacifier, if there's some other modifier to the glaze. This is the proper way. And the nice thing about this format is then, if all recipes are written in this format, and most of them aren't, but if they are, then you can look at the recipe, you can make some fairly direct comparisons from one recipe to another, because they all basically are in percent, okay? Now, one of the ways sometimes you'll see recipes written is in what I call parts, which means that they're some kind of quantities, but they don't equal 100%. And that was that example I gave you earlier, where I had something that was 30 and 50 and 60 equal 140. So if I had a list of ingredients and those are the numbers that went after them, that's obviously not percent, because it doesn't equal 100. It could be less than 100, could be more than 100, but this is just parts. It's just some quantities. So again, if I have a recipe that's listed like this, the first thing I should do is convert it to percent. So the first thing I should do is divide each one of these, 30, by 140 to give the percent. And in that case, it was 21.4. So I should convert, so I divide 30 by 140, 50 by 140, 60 by 140, I'll get all these decimal fractions, and they will equal 1 or 100%. That's the first thing I should do when I get a recipe that looks like that, is convert it to percent. Okay? And so all you do and it doesn't matter when you see the list of ingredients, it doesn't matter whether the total is less than 100 or more than 100. It's just arbitrary quantities. It could be pounds, it could be grams, ounces, doesn't matter. It's just divide each individual one by the total, and that will convert it to percent. And you can check it, because when you do that, the sum of all these things that you divided should equal 1 or should equal 100%. If they're decimal fractions, like 0.214, then it should equal 1. Okay? Everybody with me on that? Okay. The other way you'll see a recipe written sometimes is by volumes, which is about the worst possible way you can have a glaze recipe written. And it'll be like teaspoons full or cupfuls or handfuls or something like that. That's the worst possible way, because if you think about it, a teaspoonful of one ingredient is not always going to weigh the same amount. Depending on where you get the ingredient from and the source, a teaspoonful of an ingredient might be very heavy and dense and packed powder from one source, and the same chemical from a different supplier might be light and fluffy. So volume is a terrible way to do glaze recipes. You can't do precise chemistry with volume. But if you get a recipe that's like that, and I see a lot of them in publications that says, like 3 teaspoons of this and 2 teaspoons of that, or 3 cups of this, or a quart of that and 2 pints of this or something, is if you're going to do it, is that go ahead and make up the glaze, but when you're weighing it, when you're doing the volume, let's say you take the scoop or whatever it is, take the amount they want, let's say 2 teaspoons, but then weigh the 2 teaspoons. So you make it up according to the recipe, do the 2 teaspoons of the recipe, but also weigh the 2 teaspoons and record what the weight is. and then go through the whole recipe like that. And that way and if the recipe works, if it comes out okay, now you've already converted it to weight, and you can convert it to percent. So you weigh out the 2 teaspoons and it weighs 51 grams, and you weigh out the next one, which is a cup of something, and it weighs 140 grams. Then you've got it in parts by weight. So then you divide each one by the total, and now you've got weight percent. So now you've got a weight percent formula for a glaze that works. And the reason why I say it works is it may not work, because when the recipe is given in parts, if the person that made it up, let's say they had whiting, which is a fairly common glaze, if their stuff was really, really dense and they used a cup of whiting, and your whiting happens to be really, really fluffy, and you put in a cup of whiting, you don't have as much whiting. So the glaze it's very easy, the glaze might not come out the way they said it did just because of the difference in the raw materials. But that's why I said if it comes out and you like the way the glaze came out using the parts and your raw materials, now you've got a recipe by weight or by percent for your raw materials, and that'll be a useful recipe then, okay? And then also, when you have it in weight percent, then you can look at 2 recipes side by side and say, oh, this one has more feldspar than that one, so maybe that's why it melts higher. So there's some basic conclusions you can come to, even as far as the way the glaze behaves, just by looking at the same way. It's the same thing as like for cooking. You look at something and say, okay, this bread recipe has more cornmeal in it than this one, so it's a coarser. Why is this bread a coarser texture than this bread? Well, it has twice as much cornmeal in it as this one. Well, we can do the same thing for glazes. We can look at the way the 2 glazes might behave and say, well, why does this one be, and just compare the recipes. Oh, this one has a lot more silica. Well, this one doesn't have as much of that in it. So there's a lot you can infer just by comparing the recipes, but you need to have them in the same format. And if they're all in this standard weight percent format, then it's easy. It's easy to do. Okay, any questions on that? All right, let's talk about, so that's glaze recipes in parts and weights and volumes. Here's a practical challenge. Suppose you want to make up a glaze recipe, and you look at all your materials, your raw materials that you have, and let's say you want to make up a 1,000-gram batch of this glaze. But you look at your raw materials and you realize you don't have, and you look at the recipe, you don't have one of the materials, you don't have enough to make up that recipe. But you really want to make up the recipe. So the question is, how much glaze can I make up with the amount of material I have on hand? So we'll do that. So it won't be I don't have enough to make up the full 1,000 grams, but I've got enough to make up something, and I really need to do it because I've got a show coming up and I absolutely have to glaze these pots. So I've got to get some of this glaze made up. How do I do it? Okay, so here's an example. This is the formula for a very early Chinese stoneware glaze recipe. This is like an 1,000-year-old recipe, or 2,000-year-old recipe, with slightly different materials. Pardon my back, because they've done the analysis. They can do the chemical analysis. So this is the modern recipe for it, but this is 33. Again, pardon my back here while I write these down, 30.4 and 36.0. Whiting, EPK, and silica. Really simple glaze recipe. This is a really, really common. This is the basis of most of the ancient Chinese glazes. And of course, this is percent, so this equals 100%. This is all written in percent. And then suppose I want, again, pardon my back here, I want a 1,000-gram batch. I want a 1,000-gram batch. So if I wanted a 1,000-gram batch, I'd have to have 336 grams, 304 grams, and 360 grams to give me my 1,000 grams, okay? But I don't have 1,000 grams. I've only got 250 grams of EPK. That's all I've got. So the question is, how do I figure out how much glaze I can make if I use all of my 250 grams of EPK? Well, what I do is if I've only got 200, and this would be 1,000. I only have 250, but I really need to make up the full batch 304, okay? So what I do is I divide the 250 by the 304, and that tells me what portion do I have of the amount that I want? What fraction do I have that I want? And that's 0.822. or roughly 0.8. So that means I have about 8/10 of the amount I need. Okay? So now what I can do is I can take the 0.822 and multiply it. So this is the I only have this amount, 8/10 of what I need. But now that I know that number, I can take that number and multiply it by all the others and say, well, what is 8/10 of the 336? And what is 8/10 of the 360? And that tells me the amounts I need. Everybody follow that? Because I don't have as much as I need. Well, how much do I have of what I need? I have 250, and I need 304. So I have 250 out of 304, which is roughly 8. Let's call it 8/10 just to simplify it. I have 8/10. So if I have 8/10 of this, then I can use 8/10 of that and 8/10 of that, and I can still make up the recipe because I haven't changed the proportions. I've just taken the same fraction of all the different ingredients. So if I multiply that out, I end up with, if I multiply the 8/10 by the 336 and the 8/10 by that, my new recipe comes out to be, because my new recipe is going to be 822. So I'm going to end up with, instead of 270, I'm going to end up with 276 grams of whiting and 250 grams of EPK, because that's what I had, and 296 grams of silica for a total batch size of 822 grams. So this is great, and I've run into this, and I ran into this again recently myself. I make up the glazes here for the studio, and I ran out, and we didn't have enough tin oxide. I thought, oh rats, I really need to make up this glaze, and I had to get it made up. So that I thought, okay, I've got to run through this myself to figure out how can I make up. I've got to get the glaze made because we're out of it, and so I didn't have enough tin to make up the full-size batch. So I said, well, so here it is. Okay. So this is really handy. I mean, a lot of the time I just say, well, then I'll just wait until I order some more. But in this case, if you really need to make it up for some reason, or you really just, you don't want to wait until you can get together and order, this will allow you to make up a small batch in the meantime and use all of what you have. Okay? Any questions on that? All righty. Okay. So that's one example. Another situation you might run into is, suppose a glaze ingredient, or you might have a reason where you're looking at a glaze recipe and you want to make a substitution for one of the ingredients that's in the glaze recipe. Excuse me, either because you don't have it, or because you might have another reason, which I'll talk about in a minute, to want to substitute a material. So this is substituting ingredients, and this is where we have to get into molecular weights, because if I'm going to substitute an ingredient for another, I need to talk a little bit about the chemistry, because I can't just throw in any odd amount. So just by way of review again, we're going to be talking about molecular weights and atomic weights. So just again, as a review, what is that? Well, the atomic weight, the atomic weight is basically, it's the weight of that atom. So just to give you an example, aluminum, what's called the atomic weight, is 27. And what that is, without getting too heavy, that's the number of protons and neutrons in the nucleus of the atom. Without getting too chemically oriented here, but the number of protons in the nucleus of an atom determines the atomic number. That tells you what the element is. And if you add the number of protons and neutrons together, you get the atomic weight. So aluminum, the atomic weight is 27. The atomic number, that's how many protons there is in the nucleus. That's what determines what element it is 13. So if you notice, in this case, the atomic number is just close to double this. That's because there's roughly the same number of neutrons as protons. So I've got 13 protons and 14 neutrons, which gives me an atomic weight of 27. Now oxygen, I'm going to show you this. These are all atomic, and then I'm going to relate it to molecular weight. The atomic weight of oxygen is 16, and the atomic number of oxygen is 8, because it has 8 protons in the nucleus, and 8 neutrons. 8 and 8 is 16, gives me a weight of 16, and the number is 8. These are this is atomic weight and atomic number. Now, what is molecular weight? Well, suppose I have this compound, This is aluminum oxide, Al2O3. Okay? So if I want to know what the molecular weight is, the weight of one molecule or one unit of this, I take 2 times the atomic weight of aluminum and 3 times the atomic weight of oxygen and add them up. So, that equals 102. So 2 times 27 plus 3 times 16 is 102. So this is, you can think of this as a molecule. This is a unit of structure or a unit of the compound. So if I take the atomic weights of all the atoms that are in it and add them up, I get the weight of this molecule, or this group of atoms, which is called the molecular weight, and that's 102. So let's give a practical example. Suppose, this one is used fairly commonly. Suppose I have a glaze recipe that contains a lot of clay, a lot of kaolin. Well, as you may or may not realize, if you have a glaze recipe with a lot of kaolin and you apply the glaze onto a pot, there's a good chance it's going to crack and fall off the pot, or it might crawl when you fire it, because clay holds a lot of water, and so when the wet glaze is on the pot, the clay holds a lot of water. It shrinks, and so if the glaze shrinks a lot while it dries, it could flake off the pot. Or if nothing else, it can cause crawling later on. The same kind of shrinkage can cause crawling later on when the pot is fired. So you might want to say, well, gee, I love this glaze recipe, but it keeps falling off my pots when it dries. How can I solve that without changing the recipe? Well, one of the things I can do is I can substitute a different form of clay. So here's the formula for kaolin. This is the same as China clay, a really common kind of clay, okay? And this is the chemical. We're not going to go too heavily in the chemical formula, but I need to do this to explain the background. That's the chemical formula for kaolin and for most kinds of clay. 1 molecule of aluminum oxide. The dot basically means plus or together with. 2 molecules of silica. This is silica. And 2 molecules of water. It actually contains water in the clay. Now, I don't know whether you've heard the term calcine. To calcine means to heat something to bring about a chemical change. And one of the raw materials you can buy is called calcined kaolin. And this is kaolin that's been heated enough to get rid of the water. So calcined kaolin just means kaolin that's been heated. It's still a powder. It's still fluffy and powdery, but they've heated it enough to get rid of the water. So the formula for calcined kaolin is this. No water. Well, the great thing about calcined kaolin is it doesn't absorb a lot of water like normal clay, and therefore it doesn't shrink and crack when it dries. So what you can do is, the approach is, if I have a glaze recipe that contains a lot of kaolin and it tends to shrink and crack a lot, or it tends to fall off the pot or cause crawling, I can substitute part of the kaolin in the recipe with calcined kaolin. The chemistry is the same. It won't change the chemistry at all, but now the glaze doesn't shrink and crack. Okay? And the reason why I say the chemistry hasn't changed is because if I have a recipe that contains kaolin, when I heat it up, this water goes away. So the only thing that actually is left when the clay is heated, when the glaze melts, is that. So if I substitute, when I heat up the kaolin, that goes away. Well, I can substitute that. It's giving me the exact same thing, and now I don't have the shrinkage problem and the water absorption problem. So the question is, because these are different a little bit because of the water, how do I know how much calcined kaolin to substitute for kaolin? Okay, that's the challenge. Because I can't just swap it directly, because this contains water, so the weights wouldn't be exactly the same, okay? So what I do is I want to substitute calcined kaolin for kaolin. So this is where I need the molecular weights, okay? So what I do is I take the molecular weight, MW is the abbreviation, molecular weight of the calcined. I say, what is the molecular weight? Well, molecular weight of calcined is 222.2. And I got the molecular weight of calcined kaolin by adding up 2 aluminums, 3 oxygens, 2 silicons, or 2 silicons and 4 oxygens, okay? Added it all up. This 2 here, in case you're not used to reading 4, this means 2 times everything. So this would be 2 aluminums, 3 oxygens, 2 silicons, and 2 times 2 is 4 oxygens. Everybody follow that? So I add that up and I get 222. So I divide the molecular weight of calcined kaolin over the molecular weight of what I'll call the raw, which is this. And that is 258.2. And it's more. Why is the molecular weight of the raw more? Because it contains the water. So this difference is the additional weight of the 2 water molecules. 2 times 2 is 4, hydrogen is 1, and 2 times oxygen. So that's why this molecular weight is higher than that molecular weight, because that contains the water. Make sense? Everybody follow that, right? So this molecule is heavier than that molecule because it contains water. It contains something extra in it. So if I divide those 2, so I'm basically saying, how does the weight of the calcined compare to the weight of the raw? Well, it turns out it's 0.86. That's the fraction. Or you could say it's 86%. So what I can say is the weight of the calcined kaolin is 86 per molecule is 86% of the weight of kaolin. It's less. So that tells me how much I need to do. I take the weight of kaolin. If I wanted to completely replace all the kaolin with calcined kaolin, I take the weight in the recipe and multiply it by 0.86, and that's how much I use. Because I don't need, if I'm going to completely replace the raw with the calcined, I don't need as much weight because the stuff is lighter. So I don't need it the same weight. I use less weight of the calcined material, and it's less. It's 0.86. So this is a case. Well, there's a good chance you probably wouldn't want to replace all of the clay with calcined clay. Let's say usually any glaze that has about 10% more of clay in it, you have to start thinking about, are these shrinkage things going to be a problem? They're not necessarily, but they might. When you get up to like above 10%, you can start to have some of these issues. So let's say I have a glaze recipe that has 20% clay in it. And you see that I've got shrinkage problems and drying problems. So what you might say is, okay, I'll replace half of the clay with calcined kaolin. So in that case, I'd take half of the required amount of kaolin and multiply it by 0.86. So in my recipe now, I'd have half, whatever the weight is, of half the weight of raw, and then half the weight of raw times 0.86 of the calcined. And I've replaced half of the weight of the clay with calcined clay. That still gives me exactly the same chemical ingredients. I haven't changed a thing, but I've solved or I've reduced the shrinkage and the water absorption and all those other problems that come with high clay content. Everybody follow that? But in this case, I had to get into the molecular weights because I've got to look, because when you're making up a glaze recipe, I care about actually what atoms are in there, what are the elements that are in there, and how much is in there. So I actually have to start counting atoms and adding up the amounts of atoms in order to know that I'm getting the same chemistry. If I put in something that had a different formula, that let's say had a different amount of aluminum oxide, I wouldn't have the same formula anymore. So in this case, I don't want to change the formula, I just want to change the nature of the raw materials. Okay? So this is a fairly common thing that people do. The other thing that's kind of interesting, you notice this 0.86, because what that says is that the water is 14% of this. That's how much weight, when you bisque fire clay, that's how much weight it loses when you bisque fire it, roughly, is 14%. Because when you bisque fire the clay, you're driving off that water. Okay, that's one example of replacement. Suppose, let's do another one. Now this was pretty straightforward because all I did was I had to get rid of that. But suppose I'm going to use something and this hadn't changed, but where the proportions are a little different. Suppose I have a recipe now that calls for copper oxide. This is CuO. This is black copper oxide. Black copper oxide. And suppose I don't have any black copper oxide. But what I do have is copper carbonate. Now I'm going to give you a qualifier here because the chemical that we normally call, I'm simplifying the formula for this example of what copper carbonate is. It's generally not what I'm going to show you here, but I'm simplifying just to show you the principle. But suppose this is an example. I'm making up the recipe. This is just a colorant. So I've got the recipe and I just realized, oh, I don't have copper oxide. All I have is copper carbonate. Well, I can substitute one for another, but they're not exactly the same material. So the copper carbonate, I'm going to use this very simple formula of CuCO3. That's not generally what it is, but this keeps the example a little simpler. So basically, I want to use copper carbonate instead of copper oxide. Okay, so I'm going to do the same thing. Now, when I put copper carbonate in, I can write this formula in a different way. You notice, like in one molecule of copper oxide, there's one atom of copper, and in one molecule of copper oxide, there's one molecule of copper. So that's good. There's just this extra stuff. There's this carbon dioxide in here. So I can do the same kind of thing I did before if I take the molecular weight of copper carbonate and I divide it by the molecular weight of copper oxide. I can see how does it compare. Well, the molecular weight of, molecular weight of copper carbonate is, the molecular weight of copper carbonate is 123.5, and the molecular weight of copper is 79.5, which equals, now it's heavier, 1.55. It's a number, whereas before it was less than 1, like remember last time it was 8.6? So that means now, if the recipe calls for, not MV, motor vehicle, if the recipe calls for a certain weight of copper oxide, I want to multiply that weight times 1.55, and that's the weight I need to use of copper carbonate. So I did this one only because this fraction came out a higher number. The last time when we did the calcined kaolin, it was 0.86. I didn't need to weigh as much. In this case, I'd have to weigh out more of the material I'm substituting. Same idea. Let's do one. I've got one more here. I don't want to go into this too heavily, but I want to give you the idea of, suppose now I don't get the same amount of copper from the substitution. Like this is easy because I still get one of these, one copper for that and one copper for that. But suppose that's no longer true. So suppose now, this is the formula for black copper oxide, which is what we just had. Black copper oxide is CuO. But there's also another form called red copper oxide, which you can buy. It's another raw material, and that's Cu2O. Well, suppose I want to replace red copper oxide with black copper oxide. The recipe calls for red copper oxide, but I don't have any. But I've got black copper oxide. So what do I do? Okay, so I can look at it this way. I can say let me see here. Now I've got to do a little calculation here. So I'm going to say the grams, I'm going to write this up, the grams of red in the recipe I'm going to divide the number of grams that it calls for in the recipe divided by the molecular weight of the red is going to tell me how many molecules of red I need. Okay, if the recipe calls for a certain number of grams of the red copper oxide, and I divide that by the molecular weight, that'll tell me how many molecules of red copper oxide I need. Everybody follow that? This is the grams. This is the weight of one. The molecular weight is the weight of one molecule. So if I have weight divided by the weight of one molecule, it tells me how many molecules I need. Right? Okay? But each molecule of red contains 2 molecules or 2 atoms of copper. Right? So if I want to find out how many moles of, so if I multiply, I have to multiply that by 2 to give me the number of molecules of copper I need. Everybody follow that? This tells me how many molecules of this I need. I divide the total weight by the weight of one molecule, tells me how many molecules of copper oxide. But each molecule contains 2 coppers, so I have to multiply that times 2 to give me the number of molecules of atoms, sorry, I said molecules, the number of atoms of copper that I need. Everybody follow that? I take the weight of copper oxide that I need in the recipe, divide by the weight of one molecule of copper oxide, tells me how many molecules the recipe is requiring. But each molecule, each one of these molecules contains 2 coppers. So I have to multiply times 2 to tell me the number of individual atoms of copper I need. Because I have to count atoms now because the formulas aren't the same. Okay? So this is the number of atoms of copper that I need. Well, I can get that number of atoms from the same number of molecules of black, because that only has 1 per 1. Everybody with me on that? Okay. So what I can do here is so that tells me the number of atoms. So the number of atoms here is the same as the number of molecules I need of the copper oxide. So I can write this formula. I can say the molecular weight, let's see, the molecular weight of black times 2 over the molecular weight of red, which equals 79.5 times 2 over 143, that's the molecular weight of red, equals 1.11. Okay, so if I'm going to talk about molecules of red, I have to use 2 molecules of this to get the same number of coppers. So I use the molecular weight of black times 2 over the molecular weight of red, which gives me 1.11. So what I would do here is I take the weight the recipe says of red copper oxide, multiply it times 1.11, and that's the weight I need of black. And I had to do this little comparison here because I no longer have the same amount of copper in the 2 things I'm substituting. So I have to compensate for the fact that molecule of that contains 2 coppers. It's the coppers that I really care about, not the number of molecules. It's how many actually atoms of copper am I trying to get. That's why I have to do this little thing with a 2.
We hope you're enjoying the show. Please take a moment to leave a 5-star review on your podcast platform of choice. It really helps new listeners find the show. Don't forget to subscribe to receive updates as new episodes are released. And if you'd like to support the video and podcast production of the Potter's Roundtable, become a patron. Go to patreon.com and search for the Potter's Roundtable. Your support will help us achieve our goal of creating a digital library spanning the ceramic arts for use by educators and artists alike. Thank you for your support. Now let's get back to the show.
Now, there was only one other situation. I'm not going to go into this in detail because I didn't want to overly emphasize this, but I wanted to mention just another possible situation. In this case, I can still substitute one ingredient from another, but there are situations where I might have to substitute one ingredient and then make some kind of compensation for the fact that something else is going on. And I'll just describe the situation. I'm not going to go into the math. But this is a very common situation. There's a mineral called petalite, which is a fairly common, well, I take that back. No, don't listen to that. It's not common. But it is a glaze ingredient. It's not as common as it used to be. And the formula is this. It's a source of lithium. It's a natural mineral, and it's a source of lithium. Petalite, it's a mineral, and it contains 1 molecule of lithium oxide, 1 molecule of aluminum oxide, and 8 molecules of silica. Okay? Now there's another more common mineral called spodumene that you may have heard of. And it's also a source of lithium, but the formula is slightly different. And again, you run into this fairly common. So it's exactly the same, except that it only contains 4 molecules. In each molecule of the mineral, it only contains 4 molecules of silica instead of 8. So what happened, and petalite is not that common, a raw material, but it used to be used in a lot of glaze recipes. So you get a glaze recipe that you really like, and it calls for petalite, and you go, well, I don't have any petalite, but I've got spodumene. Well, I can substitute for it. But here's the trick. If I substitute spodumene for petalite, then I'm not putting in as much silica, right? So I have to add additional silica. So I can go through the calculations that we just, because this part is the same, so I'm getting the same, that's the same, and that's the same. So, but if I substitute this directly for that, first of all, the weights are different. I have to do the molecular weights, but I have to add, in addition to substituting spodumene for petalite, I have to put in additional plain silica to make up for the silica that I'm not adding. In some cases where you're making a substitution, then you have to do something else in addition because there's something else going on. In this case, you need to add extra silica, or you really significantly change the glaze by not having that silica in there. Okay? Just as a side point to this, I did this exercise a while back for a glaze, and one of the problems that you run into with glazes, not to get off on glazes, but is that the influence of impurities in the raw materials can have a significant effect on color. And so when I had this glaze that I made it up with petalite, and then I substituted and made it up with spodumene, and the color they were both green, and the color was not they behaved the same, but the color was not exactly the same, because the impurities in the spodumene were not the same as the impurities in the petalite, and that was enough to change the color of the green. In this case, this was kind of a blue-green, and this came out more of a slightly yellowish green. Not hugely different, but enough that if you put them side by side, you can see they were not the same. So just something else to consider is that when you're doing some of these substitutions, you may be changing other things like color because of impurities. We don't use chemically super pure raw materials because we're using minerals. We don't use the most expensive materials. So there's always the influence of the impurities. So even though you make the substitution, it might work about the same, but it's not necessarily going to be exactly the same because of the influence of impurities. So here's another example. Suppose I want to add an ingredient. These are a little more practical. I want to add an ingredient to a liquid glaze. I've already have a glaze that's liquid. It's in the bucket, and I need to add something to it. Let's say I want to increase the amount of silica in it. Or I left the glaze, a material out entirely, and they go, oh God, I made up the glaze, and it's in the liquid, and I've used part of the glaze or something, and I want to add something to it, and I don't know, how do I figure that out? How do I add something to a glaze that's already in the liquid glaze? So the first thing, and this might be a bucket of glaze that maybe you have a bucket of glaze around the studio that you've used, and after you've tested it a number of times, you don't like the way it works. And you go, okay, well, I need to change the recipe. I need to do something to it, but it's already in the bucket, and I don't know how much I've used, so what do I do? Well, the first thing I need to do is I need to determine what's called the solids content of the glaze. How much water versus how much solids do I have? So what I can do is I'm going to take a small sample of the liquid glaze and weigh it, and then I'm going to dry it out and weigh it again, okay? So I take the dried weight, and it could be a cup or a small quantity, but I take a scoop of glaze and I weigh that liquid glaze, and then I dry that glaze out and I weigh the dried powder. So then I take the dried weight and divide it by the liquid weight, and I get a fraction which is the percent solids. Because the dried weight is only the solids part, and I divide it by the liquid weight, which is the solids plus the water, and that tells me what percentage of that weight is solids. So it might be, like, I'm making some number like 65%, something like that, which means that 65% of the weight of that that liquid glaze is actually the solid powder, and the rest is water. Okay? So then the second thing I do, once I have this, is I weigh the full amount of glaze now that I've got in the bucket. So now I weigh the bucket, and you can, so you weigh the bucket, pour the glaze out, weigh the bucket itself, so you have the weight of the bucket. And now I know the total weight of the stuff I have in the bucket, and I multiply that by this fraction. Now I've got the total weight of solids in the bucket. I've got the total amount of powder that I've got in my bucket. So now if I'm adding a new ingredient, how do I know how much to add? So let's see, if I'm going to take, okay, so if it's going to be a new, I'll take the weight of the addition divided by the total solids weight plus the weight of the addition equals the weight percent of the new ingredient. So if I add some, if I weigh out, let's say I'm going to add 100 grams of bentonite or something. I take the 100 grams of bentonite and divide it by the solids weight that I had in the bucket plus the 100 grams of bentonite, and that tells me what the percentage is going to be when I've added that new ingredient. So let's say I haven't added any bentonite to the glaze, and I go, oh, gee, I need to add some bentonite. So I'm going to add 100 grams of bentonite, let's say, to the glaze. So I'll take the weight of the stuff that I'm going to add, divided by the new total, which is the solids weight plus the stuff I'm going to add, and that will tell me the weight percent of my new ingredient and what's in the bucket. Okay, another quickie, got a couple here. I don't want to keep you too long. Specific gravity for glazes. Have you all heard about the way that basically specific gravity is used for liquid glazes? Specific gravity is the definition of specific gravity is the weight of something compared to the weight of an equal volume of water. That's the definition of specific gravity. The weight of something compared to the weight of an equal volume of water. Specific gravity tells you the weight of something compared to the weight of an equal volume of water. Well, in a liquid glaze, I have a mixture of water and solid powder, right? And the solid powders are always a lot heavier than the water. So if I can take a small sample of glaze and weigh it, and this is used, basically what you're trying to do is, if you are making up a glaze and you've added a certain amount of water to the powder and you've got it into a perfect consistency, you really like, it's not too thick and it's not too runny, and you say, well, this is great. Everything I'm dipping or I'm glazing is working out great. How can I repeat this every time I do it? This is where you can use this idea of specific gravity. And the easiest way to do it is take a small quantity of the glaze and weigh it. Doesn't matter, take a cup or whatever the quantity is and weigh it. And then the next time you make up the glaze, take that same quantity of the glaze and weigh it and see how the weight compares to what you got when you knew it was really good. If the weight is less, it means you have more water the second time, right? And if the weight is more, you have more of the powder the second time. You follow? Because the water weighs less. If the weight is less, it means I have more water and less powder. So if I want to get, if I have my reference the first time when it was perfect, and now I weigh it the second batch and it's lighter weight, I go, uh-oh, I got too much water. So if I had to, I could add more powder to bring up the weight for that quantity the same, or if I had to, I could skim some of the water off, but I know I've got too much water. Or if the weight is heavier than what I got the first time, then I say, okay, I can still add more water to bring it to make the weight for that quantity lighter until I match the number. Then I know I've got the exact same proportion of powdered chemicals and water, and my consistency is going to be the same. The runniness or the viscosity is going to be the same. So I'm going to get the same thickness. Because we care, if the glaze is thicker and I dip a pot into it, I'm going to get a thicker glaze application. So, when you finally get it, and every glaze is different, so if I finally get it to the point where I love the way this glaze applies, I'd say, this is the way I want to make it up every time. Maybe this time it happened by accident, but the next time I want to go right back to this. And if I compare those weights, that's how I can do it. And I'm taking advantage, what I'm doing there is I'm taking advantage of specific gravity. I'm taking advantage of the fact that I'm comparing the weight of the two different amounts of that's the simplest way to do it. A couple more things here, and then we'll wrap it up. Let's talk about fired pottery. One of the common things that's nice to know about different, especially if you're using different clay bodies, is how much does the clay body shrink? And this is important for, I mean, if a clay body shrinks a lot, especially if, let's say you're developing your own clay body, you don't want a clay body that shrinks a horrendous amount, like 20%, because when you dry it and fire it, because it means that you're going to get much greater chances of warping and cracking and distortion and problems with firing if they shrink a lot. Typical clay bodies, like for cone 6 and cone 10, shrink about in the, I'm going to say 10 to 13% range. That's acceptable. But if they shrink a lot more, what happens is, let's say you have a clay body that shrinks 20% when you dry it and fire it. If one part of the pot starts to shrink or more than another, at that high rate of shrinkage, the pot can tear itself apart because the whole pot can't shrink. One part starts shrinking sooner than the other, and you get cracking or warping or distortion. So too much shrinkage is really just difficult to deal with. 10 to 13% is something we can deal with. And when I'm talking about shrinkage, it's a combination of how much it shrinks when it dries, plus then how much it shrinks when you high fire it. That's that. When they talk about the percent shrinkage of clay, that's what they mean. From the total amount it shrinks from when it's wet clay to when it's been fired. The typical thing that happens with the clay is, let's say the clay shrinks 12% total. That's what and a lot of the manufacturers will tell you if you buy a commercial clay body what the shrinkage is. Typically, that means it's going to shrink about 6% when it dries, and probably almost nothing when you bisque fire it, maybe 0.5% or less, and then the rest, 5.5 to 6, is going to be during the high fire. So you can almost neglect, not completely, you can almost neglect the shrinkage during the bisque and just say it's roughly 50-50, roughly half drying and half firing, half high firing. Okay? But one of the things I do, and so let's say you want to do sculpture, or you're doing work where you actually might want to combine clay bodies. And especially if you're making your own clay body, it would be useful to be able to determine what is your shrinkage, or even check it. I've had clay bodies that I've gotten commercially, and they seem to be shrinking a lot more than what they were claimed, and so I wanted to be able to check the shrinkage myself. And so an easy way to do is you can roll out a slab and you make up little bars. These are like 5 inches long, and you make a mark on the bar that's 10 centimeters. Yeah, here we go. Shrinkage bars that look like that. Okay? Everybody seen one of these? Well, why don't you pass those around? So you make up a little bar about 5, and you make up a mark, and this mark is 10 centimeters long. And you roll these up out of the wet clay slabs, and you just need a little line drawn into it and scratched exactly 10 centimeters. And the reason why it's 10 centimeters is because that's 100 millimeters. Here we go, metric. That's 100 millimeters. Well, that's great, because that means if I measure the line, for every millimeter it shrank, that's a percent. It's just really, and you can measure fractions of a millimeter. You can estimate them pretty easily. So you make up these little bars, and you measure them right away. You make them when they're wet, and then you dry them out and you measure them again, and then you get your drying shrinkage. And then you high fire them and you measure them again, and you get your total shrinkage. Okay, so if I take the final, I'll take the starting size minus the final size, dividing by the starting size, gives me percent shrinkage. The starting size, which is 10 centimeters, by the final, so let's say the final size is 9.2 centimeters. So the difference there is 0.8 centimeters divided by the starting size of 100, and that gives me my percent shrinkage. And this is really handy. As I say, I've done this with commercial clay bodies where the thing, and again, there's no guarantee that a commercial clay body is perfect. And I've gotten commercial clay bodies where they just didn't seem to be, they seem to be shrinking more than what I would have expected compared to other clay bodies. And so I'll go ahead and make up some shrink bars and I'll check it and I'll go, well, you know, it's 15%, it's not 10%. And that's enough to make a difference. So this is a handy thing to be able to do, especially if you're making up your own clay body, or like a lot of people are getting interested now in using local clays that you can dig up out of your backyard. One of the first things you might want to find out if you do that is, what's the shrinkage? Is this stuff, is it even going to be usable, or is the shrinkage going to be so high that I can't use it? Okay. Another thing that you might want to do with fired clay is you might want to determine the porosity. How porous is it? And this is primarily useful for functional work. Generally, you don't want to use clay that's going to absorb a lot of water. For one thing, like if assuming you're firing it like in cone 6 or cone 10, you don't want a lot of water being absorbed in the clay. It might be because you're using it for outdoor sculpture, where you want it to be weather resistant so it can't absorb a lot of water, or you don't want the clay to be porous and absorb like food juices and things if it's functional work or something like that. So if you want to determine how porous is the clay when it's all done. So what you can do is you take a piece of clay and you measure the dry weight of that piece of clay. This is what I usually do is I'll do it on one of these little bars at the same time after I do one of these shrinkage measurements. I'll take a bar and I'll weigh you weigh the bar or you weigh the piece of clay, and then I soak the clay in water or boil it in water. Actually, it works better if you boil it. Put it in a pot and boil it for like 15 minutes. Just a gentle boil.
A piece of bisque?
Yeah, piece of bisque. Okay. Or whatever, or your final fired clay. Not necessarily just bisque, your final clay. Okay. And then you take it out of the water, you wipe the water off the surface so it doesn't have beads of water, and you weigh it again. So now what you're doing is you're weighing the clay plus the water that's been absorbed in the bar. Okay? You subtract the dry weight from the wet weight, and that gives you the weight of water now that's in the bar. And you divide that by the dry weight. So the wet weight minus the dry weight divided by the dry weight. Wet weight minus the dry weight divided by the dry weight. Yeah, the wet weight minus the dry weight divided by the dry weight, because the wet weight minus the dry weight, that's the weight of water, right? That's the weight of water. So the weight of water divided by the dry weight gives you the percent of water absorbed. And generally, for most functional work, you want that to be around 3% or less. And if it's a lot, and you're probably familiar with like red clay, terracotta pots, and the fact that they don't survive, for instance, outside in the winter, because if clay absorbs a lot of water, then when the water gets into it and it freezes, it cracks apart the clay. So if the absorption is less than about 3%, it means it's going to be durable. You don't have to worry about freezing and thawing. It's also not going to absorb a lot of water in terms of getting, like if you're using it for food. That juice can't be, food juices and things can't be absorbed into the clay. I've had, as an example of that, I've had pots where earthenware, when you wash them, the water gets absorbed in the thing, and then you put it in the microwave, and I've gotten like third-degree burns from picking up a mug. I remember this years ago, I had an earthenware mug that I had been using for years, and the water had been slowly going up through the bottom, and I put a cup of tea, put it in the microwave, and I went to pick it up, and I literally got third-degree burns because the water that was in the clay heated up the mug. And I couldn't it actually burned my hand, stuck it to the mug. I couldn't let go of the mug. So that's not good. But also, if the glaze isn't perfect, even if the glaze isn't perfect, then things and none of them is perfect, then things can get down through the glaze into the clay, which you don't want. Even crazing and pinholes and things can allow water to get down into the clay. So it's better if the clay is completely, basically non-absorbent. The last thing I just want to mention briefly was, this is about kiln operation, is that People talk about, especially wood-firing people, are always where people are building their own kilns. They're always interested in comparing the efficiency of their kiln. Like my kiln's a lot more, I use a lot more wood or a lot less wood than somebody else. The real way, if you're interested in calculating how efficient your kiln is, what you really want to do is you want to say the amount of fuel that you used divided by the weight of the fired ceramics. Because what you really care about, you don't care how much fuel you used, it's how much fuel did you use to fire a certain amount of pottery. And so that's the way you can put it on a common basis, regardless of the size of the kiln and whatever. It's how much fuel did I burn versus compared to what's the weight of pots that I fired. And that's a really good way. And so like you could say, well, how many cords of wood? I used 10 cords of wood and I fired 300 pounds of pots. And that completely eliminates all the effects of the size of the kiln, and that's a direct comparison of efficiency. And you can do the same thing with electric kilns. You can say like, well, how many kilowatt hours did I use? You can get that off your meter. How many kilowatt hours did I use to fire this load of pots, and what's the weight of clay? Because when you're firing a kiln, you're heating up the kiln, you're heating up the shelves, the furniture, you're losing heat. Kilns are horribly inefficient. They all are horribly inefficient. But if you're interested in comparing it, what you really want to know is how much energy did I use to heat up a certain amount of pots or a certain weight of clay. That's what you really want to do. And that's the way to put it on a common basis. Okay? Well, thank you very much. Now, as I say, next month I think we're going to talk about what I'm going to do is I'm going to go through sort of the step-by-step, the processes that we use to make ceramics, and then how do the laws of physics come in, or what's really going on from a physics point of view when we're doing one of these steps.
The Potter's Roundtable is brought to you by Washington Street Studios and our patrons. If you enjoy the show, please subscribe, give us a 5-star review, and tell your friends. If you want to learn more about Washington Street Studios and shared studio memberships, please visit our website at www.hfclay.com. Thank you, and we'll see you again next time on the Potter's Roundtable.